Hi, I'm Chris from Team 19961 based in Shenzhen, China. In this video, I'll be introducing my most passionate extracurricular, my robotics project. Since elementary school, I have had experience in the first LEGO League where I explored simple robotic structures and ideas. Later, I went through training in Python programming and competed in the American Computer Science League. And when I eventually attained the ability to take on more advanced projects, I joined Bay Dynamics Robotics Club, where I competed in the First Tech Challenge. My first encountering with the FTC was in the summer of 2020, when I became a member of this club. I began with the basics of utilizing parts to construct a robot and Java programming, and then progressed through modeling with Fusion 360 and trying out advanced algorithms, gaining more working experience. In the Ultimate Goat season, I participated as a programmer, handling the majority of both manual and autonomous codes. Later, through speed build off-season challenges in our club to further enhance my capabilities, and one more season of participation, I was finally selected as an operator on the field. In the 3+ years of competition, our team has achieved multiple Champion Alliances Inspiration Awards in both offline and remote tournaments.
The season of 2021 to 2022 Freight Frenzy was when I genuinely felt inspired, and for the rules of that season, please see the link in the description. Our team consisted of 7 people then, and because each of us possessed a variety of interests and strengths, we divided ourselves into 2 major groups, specifically engineering and programming, and the development of the mechanical structures were majorly contributed by the teammates. The biggest highlight of the architecture is the implementation of modular design, which allows for the easy separation of chassis, turret, and superstructure. For the chassis, we installed 3 additional encoders to establish full orientation of the bot during the autonomous period. The turret was powered by a continuous spinning servo and replaced the need to rotate the chassis when aiming for collection or delivery. The double slides in the superstructure also substituted for the functions of the chassis movement, which boosted efficiency. A basket was placed on the end of the slide and hosted the use of both intake and delivery. An additional mechanism in the superstructure was the friction wheel for spinning the rubber ducks. The reason that we chose to design such mechanical structure was to suit our most efficient scoring plan. Through internal discussions and experiments, it was discovered that for us to save more time on actually scoring, our chassis had to perform the least movement as possible. Therefore, except for the necessary entering and exiting the warehouse, I proposed to depend on turrets and slides as replacements. Additionally, we found out that an intake and output integrated system would drastically reduce the possibility for mistakes and lower our workload. In fact, the advantages in our design and strategy won us outstanding results in competitions, such as the Inspiration Award in China Remote Qualifiers and Design Award in National Remote Championships. However, an ingenious hardware design does only half of the job, while an elaborate software program is equally crucial, especially in the autonomous period where scores are worth much more. In the 30 seconds of the autonomous period, I built a logic framework consisting of sequential execution of events, namely visual recognition and payload delivery. Then, a looped section of additional cargo delivery until the timer forces the bot to park. One subsystem in the framework was the preload delivery, which challenged us with the requirement of high accuracy. In order to improve precision, and also taking into account from failures in the previous season, we adopted the method to measure difference in RGB data provided by the camera and a few sampling points. We measured the color difference in specific channels of every bar in the barcode and that of their surrounding environment. And the advantage of this method is that it mostly ignores the impact of the light environment on the results. For additional cargo delivery, I designed a cyclical series of actions including moving to the warehouse, conducting intake, exiting the warehouse, and final delivery. And while those are happening, 3 separate PID systems work in parallel with improvements. And those are the turret PID, slides PID, chassis PID, and a 30 seconds timer to remind the bot to navigate and park in time. Embedded within the subsystem are 2 subsystems which will kick in when encountering certain situations and work as backup. The intake subsystem resolves the issue in the initial extension of the slides of not touching or grabbing a cargo component. In the flowchart, if the touch sensor indeed didn't detect the presence of cargo, it would trigger the backup plan on the right of the diagram. At first, the turret would rotate to a designated angle, and if the sensor still hasn't made detection, the slides will extend further while the turret continues swinging. This action pushes the intake mechanism deeper into the pile of cargo in the warehouse, where there is simply more cargo pieces to be taken, and thus making the solution stably effective. The final delivery subsystem works in similar manner, but what's different is that in our earlier versions of the program, we didn't include the codes nor sensors for aiming adjustments. Nevertheless, during experiments, we noticed that the turret couldn't always be aligned with the hub, and often leading to the cargo drop close but missing the target. To counter the problem, I suggested to add distance sensors for detecting the hub on the basket and wrote designated algorithms for the situation where the bot is unable to detect the hub tray. In those cases, the turret will veer left then right to suitable angles and only drop off the cargo until sensing the tray, making sure the precision of each delivery. During the season, not only do me and my team have to tackle problems in the procedures of the mission, but as well as creatively refining flaws in the basic while crucial components of the bot. For example, in early tests, the chassis often bumped into obstacles when accessing the warehouse and couldn't go in a straight line. I first tried to adjust the drive constants in our chassis PID and adding offset values to the motors, but the problem remained. Through heated discussions, the engineering group suggested to mount ballast to the chassis, which could potentially balance the weight distribution. At last, I adopted the plan, and after numerous test runs, the situation did improve.
Through this season of FTC that I participated in, I think it is obvious to see that nothing is smooth sailing. There has been so many difficulties, challenges, and failures on the way, but I really love how I could resolve all those issues together with friends, while also enjoying the achievement that's brought along. Most important to note is that as a captain, I could feel the duty, power, and responsibility that this position holds, and the opportunity to truly and deeply participate in this program that I love. Currently, I am preparing for the FTC 2024 season center stage, and stepping towards a world championship. Last but not least, I really wish to continue this passion of robotics in high school in the future. Thank you for watching.